everyone, I am Dr. Shimpi Ralhan from Sri Shankaracharya Technical Campus, Bhilai. Welcome to the NPTEL course on Industrial Automation and Drives. Today we'll have a lecture on Basic Fundamental of DC Machines 1. In the previous lectures, we have already discussed the basic concepts behind the working of electrical machines such as electromagnetic induction, Faraday's law and Lenz's law. We have also seen the magnetic circuits and the related terms such as magnetic flux, flux density, permeability, etc. Today, we'll explore the construction including the stator, rotor, commutator and understand their working principle based on electromagnetic induction and review the various types including generators and motors. So, DC machines are basically categorized into two types, that is DC motors and DC generators. A DC generator converts the mechanical energy into electrical energy and generates DC electricity when mechanical motion is applied to it. And DC motor, it converts electrical energy into mechanical energy and uses electrical power to produce motion, as you can see in the figure. Now let's see the construction of DC machines. The permanent magnets create north and south poles of the even numbers, say 2, 4, 6, 8, and it is not possible to have odd number of poles and having a DC machine working. So as you can see in the side view of the DC machine, we have armature, armature winding, bearing and commutator. The different parts are being shown, and the stator is the stationary part, rotor is the rotating part with the least possible air gap between them equal to 0.5 to 2 mm. Stator consisting of yoke, field windings and poles. Next is rotor, which is also known as armature in DC machines, having armature core, armature winding. As shown in the figure, it is made up of copper, and commutator. Brushes and bearings which hold shaft, then the cooling fan which is provided to minimize the heat losses that are taking place while the DC machine is in operation. Let's see the different parts of our stator. Stator yoke. The stator yoke is the outer frame or core structure of a DC machine that surrounds the stationary part including the field windings and the magnetic core. It forms part of stator which is stationary component of the machine. It is typically made from high quality silicon steel sheets and has a usually cylindrical or ring like shape, and the overall geometry of the machine is like that. So, if we see the stator yoke, it gives stability to the machine and is used for bolting it to the ground. Next comes the field poles. Field poles have windings wound around them known as field windings through which current flows to produce the magnetic field. The purpose of the pole is to produce working flux in the machine. The pole shape is broad, as you can see in the figure, in order to distribute the flux uniformly in the air gap so that the waveform of the voltage induced improves and the air gap is also reduced. So this shape of the pole also facilitates the increase in the permeability. The pole is spread out as pole shoes to minimize the air gap, hence reducing the reluctance, spreading the flux uniformly on the armature conductors as shown in the figure. Next comes the field winding. The field winding of the DC machine consists of field coils which are made up of copper wire, as we have seen in the previous figure. These coils are wound around the slots of the pole shoes. The field winding essentially forms an electromagnet that generates magnetic field flux. The rotor armature of the DC machine rotates within this magnetic field, leading to effective flux cutting. It is very important to decide that what the polarity of a pole is, and it depends on the polarity of the excitation and orientation or the sense of the winding as shown in the figure below. The field winding on the pole core is wound in a specific direction. When it carries current, the pole core behaves as an electromagnet, and this leads to the generation of necessary flux. The field winding is divided into various coils called field coils. These are connected in series with each other and wound in such a direction around the pole cores that alternate north and south poles are formed. If the preceding pole makes magnet makes south pole, then the successive one will form north, and so on. Next comes the interpoles. As the name suggests, the interpoles are small poles compared to main poles and place in interpolar region between the main poles. These are also electromagnets and are connected in series with the armature windings through the brushes. Next comes the compensating winding. The compensating winding consists of a series of coils embedded in the slots in the pole faces. These coils are connected in series with the armature. The series connected compensating windings produce a magnetic field which varies directly with the armature current as these coils are connected in series with the armature. Next comes our brushes. Brushes are made typically from carbon or graphite, and they offer electrical connection between the rotating commutator and the stationary load as it is shown in the figure. They collect current from the winding, place on the commutator through brush holders and spring. These are, you can say, stationary sliding contacts, and brushes are in contact with both the rotating part and the stationary part. If more amount of current is to be carried by the brushes, so the number of brushes increase, and hence you can say that the brush number depends directly on the amount of current that needs to be collected and fed up in or out. So the proper brush maintenance and alignment is very essential for efficient operation and long life of DC machine. The end covers. These are the end housings that are attached to the ends of the mainframe and provide support to the bearings. The front housings support the bearing and the brush assemblies, whereas the rear housings usually support the bearings only. Now, next is our bearing. The ball or roller bearings are fitted in the end housings. The function of the bearings is to reduce the friction between the rotating and the stationary parts of the machine. Mostly, high carbon steel is used for the construction of the bearings as it is very hard material. Let us see our rotating part, that is rotor. In DC machines, the rotating part is known as armature, and in AC machines it is called as rotor. So whenever I use the word armature, it indicates the rotating part. So the main parts of armature are armature core, armature winding, shaft and commutator, as you can see in the figure shown. Now next comes the first part, that is armature core. Armature core is cylindrical in shape and it is mounted on the shaft. It consists of slots on its periphery and air ducts to permit the airflow through the armature, which serves the cooling purpose. And the slots on the periphery, they are for housing of the armature winding. Armature is made up of such a material that it allows maximum flux to pass through it, which means that the reluctance is reduced and hence the magnetic flux is linking to the maximum amount to the field winding. The shape of armature is cylindrical or drum shaped, and the material used in making armature is high grade silicon steel in the form of laminations which reduce the iron losses. Now, as we know that in electromagnetic machines, we have two types of losses, that is the iron losses and copper losses. Iron losses are again categorized as your eddy current losses and hysteresis losses. So, the eddy current losses are the losses which take place in the iron part, and by using the laminations we reduce the eddy current losses which are your iron losses only. Next comes our armature winding. Armature winding is the interconnection of armature conductors which are placed in slots provided on the armature core periphery. When the armature is rotated, in case of generator, magnetic flux gets cut by armature conductors and EMF gets induced in them. Whereas in case of motor, it carries supply current. The armature winding is divided into as many parallel paths as the number of poles. Say if number of poles are 2, then the number of parallel paths will also be 2. So, if we say that the total number of armature conductors is Z and P is the number of poles, the number of conductors per path is given as Z by P. Armature winding serves very important functions. Number 1, generation of EMF takes place in the armature winding in case of generators, and it also serves the purpose to carry the current supplied in case of DC motors. Next is our shaft. As you can see, the shaft is made up of mild steel with maximum braking strength, and it is used to transfer mechanical power from or to the machine, as if it is working as a motor or generator. The rotating parts like armature core, commutator, cooling fans, etc. are all key to the shaft. Commutator. This is a very important part of our machine, which is nothing but a mechanical rectifier. Commutator performs the function of current reversal. Now, what is this current reversal? As the armature turns or rotates, the commutator segments connected to the armature windings rotate with it. The commutator is split into multiple segments, as you can see in the figure, which are insulated from each other, and each segment is connected to a different winding. So, as the armature rotates, the commutator segments switch the current from one winding to another. This action reverses the direction of current in the windings at the appropriate time, which ensures that the torque on the armature remains in the same direction, which keeps the motor turning. So, basically you can say that commutator performs current reversal as well as it performs switching action. Now, in case of generator, commutator converts alternating voltage generated in the armature winding into direct voltage across the brushes. Depending upon the manner in which armature conductors are connected to the commutator segments, we can classify our windings into two types. Number 1, lap winding. Number 2, wave winding. The difference between these two consists in the arrangement of end connections at the front of armature. This is to be noted that this is how the classification is done, based on the arrangement of end connections at the front of the armature. Lap winding. In lap winding, the armature coils are arranged such that the ends of each coil overlap or lap over the previous coil. In the lap winding, the armature conductors are divided into groups of number of poles P. For lap winding, the number of parallel paths given by A is same as number of poles given by P. So, what we can write? We can write that A is equal to P. What is our wave winding? In wave winding, all the conductors are connected in series and it forms a single loop and appears to be in the shape of wave. For wave winding, irrespective of the number of poles, the number of parallel paths is always 2. So, what we can say here, A is equal to 2. In wave winding, a smaller number of parallel paths are available compared to the lap winding, and the wave winding is used for high voltage, low current DC machine, whereas in lap winding the number of parallel paths is more, as A is equal to P. If P is equal to, if it is a 4-pole machine, number of parallel paths will be 4 and so on. So, due to this, our lap winding is capable of supplying larger load current. So, it is used for low voltage, high current applications. Next, let us see, after seeing all the parts of our DC machine, the construction, the working principle of DC machines. The operating principle we can say is Fleming's left hand rule for motors and right hand rule for generators. All the generators work on the principle of dynamically induced EMF, which we have already discussed in the previous lectures. A DC machine, either it is a generator or a motor, generally employs windings distributed in slots over the circumference of the armature core. Each conductor lies at right angles to the magnetic flux and to the direction of its movement. Therefore, the induced EMF in the conductor is given by E is equal to BLV volts, where B is the magnetic flux density in Weber per meter square, L is the length of the conductor in meters, V is the velocity in meter per second of the conductor. So, the right hand rule for generators is that if the 3 fingers of a right hand, namely thumb, index finger and middle finger, are outstretched so that every one of them is at right angles with the remaining 2, and if in this position index finger is made to point in the direction of lines of flux, thumb in the direction of relative motion of the conductor with respect to the flux, then the outstretched middle finger gives the direction of the EMF induced in the conductor. Visually, the rule can be represented as shown in the figure. This rule mainly gives the direction of current which induce EMF in. The conductor will set up when the closed path is provided to it. So, let us see the EMF equation of DC generators. EMF gets induced in the conductor according to Faraday's law of electromagnetic induction, right? So, hence we can say that the average value of induced EMF in each armature conductor is given by E equals to rate of cutting the flux, that is d by dt of phi. Now, consider one revolution of conductor. In one revolution, conductor will cut total flux produced by all poles, that is phi into P, where P is number of poles, while the time required to complete one revolution is 60 by n seconds, as n is speed in revolutions per minute. So, substituting for numerator P phi and the denominator for time is 60 by n, will get E equals to P phi n by 60. This is the EMF induced in one conductor. Now, the conductors in one parallel path are always in series. There are total Z conductors with A parallel paths. Hence, Z by A, number of conductors are always in series and EMF remains same across all parallel paths. So, we'll multiplying P phi n by 60 with Z by A will get PZ will get P n phi Z upon 60A, where P is the number of poles, flux is the phi is the flux produced by each pole in Webers, n is the speed of armature in RPM, Z is the total number of armature conductors, A is number of parallel paths, which is 2 for wave winding and which is equal to number of poles for wave winding. So, we observe that here the number of conductors Z, they are constant for a machine, number of poles are constant, design constant, parallel paths is also a design constant. So, what we observe here is that E is proportional to N and phi, or we can say that E is equal to N, E is proportional to N into phi. Working principle of DC motors. The principle of operation of DC motor can be stated like that: when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force. In a practical DC motor, field winding produces a required magnetic field, while armature conductors play a role of current carrying conductors, and hence armature conductors experience a force. The magnitude of the force experienced by the conductors in a motor is given by F is equal to BIL Newton, where B is flux density due to flux produced by field winding in Weber per meter square, I is the magnitude of current flowing through the conductor in amperes, and L is the active length of conductor in meters. Let us see now the Fleming's left hand rule, which is used to explain the working of a DC motor. The direction of the rotation of the motor is determined by this rule. The rule states that if we outstretch the three fingers of our left hand, namely the first finger, the middle finger and the thumb, such that they are mutually perpendicular to each other, then if we point the first finger, it is in the direction of magnetic field, the middle finger in the direction of the current, and thumb gives the direction of the force experienced by the conductor. This is shown in the figure. Let us see an important concept for our DC motor, that is back EMF. What is this back EMF? Let us see that. When a DC motor is started, the armature begins to rotate within the magnetic field of the stator. Due to the residual magnetism in the stator core. Now, what is this residual magnetism? It refers to small amount of magnetism that remains in the magnetic materials, say such as pole pieces or core of the motor, even after the external magnetizing force such as excitation current has been removed. So, due to this residual magnetism in this stator core, even before the motor reaches its full operating speed and before a significant field current is established, there is a small magnetic flux present, right? This residual magnetism contributes to this small magnetic flux. This residual magnetism creates a small initial back EMF in the armature windings as the motor begins to turn, and this back EMF is given as EB phi ZNP upon 60A, right? So, this is a very important phenomena for the working of DC machine as motor. Torque equation of DC motor. The power developed by the motor, as we know, is given as the product of torque and angular speed. So, torque is denoted as T and angular speed as omega. and omega is given as 2 pi n upon 60, where n is speed in RPM. So, in the armature of the motor, the electrical energy is converted into mechanical energy, and our electrical energy, that is given as the product of back EMF and the armature current. So, equating both the expressions, what we will get, that torque is given as phi z n p divided by 60A multiplied by Ia 2 pi n. So, the torque equation of the machine, again if we see that the number of conductors are going to be constant, poles also going to be constant, then number of parallel paths also going to be constant. So, torque is proportional to the product of flux and armature current. So, if the flux increases, torque increases, current increases, torque increases, or vice versa. So, torque depends upon the flux as well as the armature current. Let us now see the classification of DC machines. The DC machines are divided on the basis of the type of magnet that is used for their construction, that is electromagnetic type, permanent magnet type. Again, for the electromagnetic type, we have further classification as separately excited, self-excited. Self-excited is again divided into series machine, series DC machine, shunt DC machine, and your compound DC machine. Compound is again divided into long shunt and short shunt. Now see, one very important thing is that the construction of the DC machine, whether it is operating as a generator or a motor, it remains same. Only the direction of the current that is flowing through the armature changes. For the generator, it is going to supply the electrical energy. So, the direction of the current will be out of the armature, whereas in the case of motor, it will be taking electrical energy as input. So, the direction of the current will be into the armature. Let us see what are permanent magnet DC motors. These are abbreviated as PMDC motors, and it is, you can say, a type of motor that uses a permanent magnet to create the magnetic field that is required for the operation. As the magnetic field strength of the permanent magnet is fixed, it cannot be controlled externally. Field control of this type of DC motor is not at all possible. So, small fractional and subfractional kilowatt motors are often constructed using a permanent magnet. This is a very important concept which we will be seeing in the further lectures for drives. That is, this motor cannot be controlled as the field strength is permanent. Now, PMDC motor is extensively used where small DC motors are required, and also very effective control is not required, such as in automobiles, starters, toys, wipers, etc. The stator is made up of permanent magnet in the PMDC motor, hence there is no need for separate field excitation for stator. So, PMDC acts as a shunt motor with fixed field. Now, let us see the classification of the machines based on which are constructed using your electromagnets. According to the method of excitation, electromagnet DC machines are classified in two parts. Number 1, separately excited DC machine. Number 2, self-excited DC machine. If we see the features of the separately excited DC machines, it requires a separate source of it for its excitation. Its field and armature windings are isolated electrically. The terminal voltage across the load given by Vt does not affect its excitation. Due to additional voltage source requirement, it is rarely used generator. Around 95% of DC generators are self-excited only. So, we can classify it into two categories: voltage excited, long thin wire having high resistance; current excited, short thin wire having low resistance. Separately excited DC generator. A DC generator whose field magnet winding is supplied from an independent external DC source. For example, a battery. It is called a separately excited DC generator. The field winding of separately excited generator has large number of turns of thin wire. So, the length of such winding is more with less cross sectional area. The field current is given as, you can see from the circuit diagram, IF is equal to VF by RF, where VF is the voltage across the field winding and RF is the field circuit resistance. The voltage equation is given by Eg equal to Vt plus Ia Ra, where Vt is the terminal voltage, Ia is the armature current and Ra is the armature resistance. If the brush voltage drop is also considered, which is, let us say, voltage drop be Vb, then the voltage equation modifies as Eg is equal to Vt plus Ia Ra plus Vb, and the armature current is given as Ia equal to Eg minus Vt divided by Ra. In generator, remember that always Eg will be greater than Vt, that is, the generated EMF will be greater than the terminal voltage. So, we have seen now separately excited DC generator. Let us see the separately excited DC motor now. The schematic representation is shown in the figure. The field current IF is given as VF by RF. Voltage equation can be written using KVL, that is EB is equal to Vt minus IaRa. Terminal voltage can be obtained from it, that is Vt is equal to EB plus IaRa, and considering the voltage drop, the equation modifies by adding Vb. Armature current can be reduced from there as Ia is equal to Vt minus Eb by Ra. In motor, remember that always your Vt will be greater than Eb, that is terminal voltage will be greater than the back EMF. Now let us come to the self-excited DC machines. In this type of DC machine, the field winding and the armature winding are interconnected in various ways to achieve a wide range of performance characteristics. For example, field winding in series or parallel with the armature winding. So, self-excited machines are further classified as shunt wound DC machine, series wound DC machine, compound wound DC machine. Shunt wound DC machine have field winding connected in parallel with the armature winding. That is why the name is shunt. Hence, the full voltage is applied across the field winding. Shunt winding is made with large number of turns and the resistance is kept very high, about 50 to 300 ohm, whereas the armature resistance has the least possible value, say 0.1 to 1 ohm. Shunt field winding takes only small current, which is less than 5% of the rated armature current, because its resistance is very high and the most of the current that goes to your armature winding. So, if we see a shunt wound DC generator, the circuit diagram is shown in the figure, that field winding is connected in parallel with the armature and the combination across the load, then the generator, then the machine is working as a shunt generator. Here the field winding, again you can see, has large number of turns of thin wire having high resistance. Let the resistance of the field winding be RSH. So, voltage across the shunt field winding will be given by V, the entire voltage will appear across it. Then the shunt field current is given as ISH is equal to Vt by RSH, and armature current will be Ia is equal to IL plus ISH. The shunt wound DC motor. In this type of DC machine, the field winding is connected across the armature winding and the combination is connected across the supply as seen from the circuit diagram. The flux produced by the field winding is proportional to the current passing through it, that is phi is proportional to ISH. As long as the supply voltage is constant, which is usually so in the practice, the flux produced is constant. Hence, we can say that DC shunt motor is called as constant flux motor. Shunt field winding has more number of turns with less cross sectional area here. So, shunt field current is given as ISH is equal to VT upon RSH. Armature current is given as IL minus ISH, and the voltage equation can be written using KVL, that is VT is equal to EB plus IA RA. So, next comes our series wound DC machines. In this type of DC machine, field winding is connected in series with the armature winding. Therefore, the field winding carries the whole of the load current or armature current. The armature current itself acts as excitation. It is termed as current excitation. As the load current completely flows through the armature and field winding, series winding is designed with few turns of thick wire and the resistance is kept very low, say about 0.5 ohm. So, when the series wound DC machine works as a DC generator, let us see its operation. When the field winding is connected in series with the armature winding as shown in the circuit diagram, the resistance of the series field winding is again kept very small, and hence naturally it has less number of turns of thick cross section as shown in the figure, and the armature current IA is equal to the series field current ISH, ISC is equal to load current IL. So, IA is equal to ISC is equal to IL. The same current flows throughout the circuit. Now, the voltage equation can be written using KVL as EG is equal to VT plus IRA plus ISC RSC. Next is our series wound DC motor. In this type of motor, the series field winding is connected in series with the armature and supply as shown in the circuit diagram, and the flux produced is proportional to the armature current, that is phi is proportional to IA. Again, the armature current is equal to series field current is equal to load current, and the voltage equation can be written as VT is equal to EB plus IARA plus ISC RSC. Next comes the compound wound DC machine. In this type of DC machine, there are two sets of field winding. One is connected in series and the other is connected in parallel with the armature winding, and hence the name compound wound, because both the sets of windings are present. And we can further divide our compound wound machines into long shunt and short shunt. Long shunt, here the field winding is connected in parallel with the combination of series field winding and armature winding, whereas in short shunt, field winding is connected in parallel with only the armature winding. As you can see in the long shunt compound generator, the schematic, you can see in the schematic that the shunt field winding is connected across the series combination of armature and series field winding. As evident, the armature current IA is equal to IL plus ISH or IA is equal to ISC. So, voltage across the shunt field winding is VT, then the shunt current can be written as VT upon RSH, and the voltage equation will become EG is equal to VT plus IRA plus ISC RSC. The long shunt compound motor has the shunt field winding connected across the combination of armature and series field winding as shown in the schematic. Now, voltage across the shunt field winding will be VT and armature current IL, armature current will be IA and IL is equal to IA plus ISC, and shunt field current will be ISH, that is VT upon RSH, and the voltage equation will be VT is equal to EB plus IARA plus ISC RSC. Short shunt compound generator. Now, please see both the diagrams here, both the circuit diagrams. Here shunt field winding is connected only across the armature excluding the series field winding. Here the series field winding is excluded. Now if we redraw the figure, we will get the second circuit diagram, and the armature current is given as IA equals IL plus ISH, and ISC will be equal to IL. So we can write the expressions for the voltage and shunt field current as shown. Again, the short shunt compound motor. In this type, the shunt field is connected purely in parallel with armature, and series field is connected in series with the combination as shown in the circuit diagram. On the similar lines, if the voltage across the shunt field winding is V, we can write down the expressions for our load current, shunt field current and the voltage equation. So, today we have discussed the construction of DC machines, working of machine as generator and motor. Also, we have seen the different types of machines based on the excitation and their elaborate classification. So, all the above discussions are important for operating electrical machines, and we'll see their utility in the next lecture. Thank you. Thank you so much.